Hey, we have here today another integral on the board. This was from the MIT Integration Bee 2022, regular season number 19. We have the integral of x squared sine ln x dx. Okay, and the first thing you may notice is that I already did this problem not too long ago. I've seen a lot of comments recently about using the complex definition of trig functions, and I haven't done an integral like that in a while, so I thought I would do one here. But before I get to any complex numbers, I want to just do a U-substitution to set this up. So I'm going to notice we have our ln x here that we need to handle. So I'm going to call that my U. So we'll have U equals ln x. And what I want to do is solve for x, just to make it a little easier on myself. So if we do that, rearranging, we could write x equal to e to the u. I'll take a derivative, and so we'll find that dx is going to be equal to e to the u du. And since I have an x squared here, let's just get our x squared value and just notice that x squared is going to be e. If I square that, it's going to be e to the 2u. So now I'll make this substitution. So we'll start with that e to the 2u. We'll have sine of u here, and then our dx is going to be this, so we're going to have eu du. And then I'll just multiply our e terms together. So this is going to be equal to e3u sine u du. Okay, and so now that we have the preliminaries out of the way, we can kind of focus on this. And what we'll do is, you'll notice that for sine u, we do have a complex definition of this, and let's just look at that right now. So for our complex definition of sine, we have this value over here to the right, and this is just easily derived from Euler's formula. And what we could do is we could take this and plug this in and integrate, and notice that then we'd have all exponential functions, and it's not too bad. Now, instead of doing this, what I wanted to do instead was let's just recall Euler's formula, which would be if we have e to the ix, this gives us cosine x plus I sine x. And then we notice if we take the imaginary part of e to the ix and the imaginary part here, well, the imaginary part of this is going to be the same as just sine x. So with our integral, what I'm going to do is take this sine u, and I can write this as the imaginary part of e to the iu. Okay, so now rewriting the integral, I've taken this like imaginary part and I've wrapped it around the whole integral. That's because everything else is going to be real, so I can just have the imaginary part of the whole thing. And the nice thing about that is the integral now is like pretty simple because we're just going to be dealing with exponentials. And of course, I can put these two together. So e3, when I multiply e3u times eiu, I can write this as e3 plus iu du. I'm just going to drop this notation for the moment so we don't have to keep rewriting it, but we'll bring it back at the end. So now just integrating this is going to be pretty easy. We're just going to get e3 plus I u, and we just need to divide by 3 plus I. And what I can do to get the I out of the denominator here, I can just multiply by 1. We can multiply by 3I over 3I, like this. When you multiply this together, you end up with 3 times 3 is 9, minus I squared, which is plus 1. So this thing's all going to be over 10. Then in the numerator, we'll have our 3 minus I. What I want to do is take this, and I'm actually going to put it back the way we had it. So I'm going to rewrite this as e3u times eiu. I'm just going to rearrange this a little bit. What I'll do is I'll write this e3u first over 10, just noticing that this part's all real. Okay, next we'll bring down our 3 minus I. And then for e to the iu, I'm going to do is put this back using Euler's formula and write this with cosines and sines now. So I'm going to write this as cosine u plus I sine u, and then we can just distribute and multiply this together. Okay, so doing that, we're going to have, first term is going to be 3 cosine u minus I cosine u. Then here we're going to have a plus 3I sine u, and then here minus I times I sine u is going to be minus I squared, which is going to be a plus sine u. And now I just want to reorder this so we have real stuff together. So this stuff here is real, and then this stuff in the middle is going to be imaginary. So when I rewrite it, we'll still have our e3u out front here. Then we'll have 3 cos u plus sine u. And then from this, what I'll do is I'll factor the I out front, and then inside the parentheses here, we're going to have 3 sine u from here minus cosine u. Okay, and just notice that at this point now we have this in like our a plus bi notation. So like, okay, this would be a, and this would be our b, a plus bi. And so from this notation, we can see that this here, this a is going to be our real part, and this b is going to be our imaginary part. So what I'm going to do now is we'll just put back this notation that I just dropped for laziness or whatever. So we'll put that back. And what that's going to allow me to do is kind of just ignore my real part. We'll bring back this as a coefficient in front, so we'll have e 3u over 10, and then we'll have our imaginary part, which is just going to be 3 sine u minus cosine u. And the only thing left we have to do is we're in u and we want to get back to x, so I'll just back substitute with my u value. And before I do the full back substitution, let's just realize, let's look at e3u. E to the 3u is going to be the same thing as e to the u cubed. And you may recall, but I erased it, that x is actually equal to e to the u. So e to the 3u, or e to the u cubed, is going to be the same thing as x cubed. So when we back substitute, we're going to have here x cubed over 10, 3 sine natural log of x minus cosine natural log of x. Put a plus c on the end, and that's it, we're done. And you'll notice, fortunately, this is the same answer that we got in the previous video. I'll provide a link to that one if you want to see a different one. I think I did integration by parts on that one, so you can check that one out. I'm not really sure if it's easier with integration by parts or with this complex method, but I think maybe this way was more fun. So anyway, hope you enjoyed it. We'll stop it there. Thanks everyone for watching. Have a great day.